In this lesson, we're going to cover Taylor polynomials and Taylor's inequality, or it's also referred to as Lagrange error bound. First, we have a definition. It says the following expression for t sub n of x is a polynomial of degree n called the nth degree Taylor polynomial of f at a. So here's the formula that we're using for our Taylor degree polynomial. And you'll notice it looks very similar to a Taylor series. It's just that it's a polynomial, so it's going to stop with its highest power of a power of n. Here we have a note. It says, notice that the first degree Taylor polynomial, t sub 1 of x equals f of a plus f prime of a times the quantity x minus a, is the same as the linearization of f at a. We will be using a Taylor polynomial, t sub n, to approximate a function f. When doing so, ask how large should we take n to be in order to achieve a desired accuracy. This example says consider the function, and we have f of x equals 1 over x. Part A says find the Taylor polynomial up to degree 3 for f of x centered at a equals 1. Graph on a common screen. So I have the chart set up. We're going to start with n equals 0, and that means we're not going to take a derivative, so we'll just rewrite the original function. So the function is 1 over x, and then in this column we're going to plug in 1 for x, so we just get 1. Next we're going to do n equals 1, so that means we're going to take the first derivative. So we get negative x to the negative 2, and then I rewrote it as negative 1 over x squared, and now we'll plug in 1 in for x. So we get negative 1. Next we're going to let n equal 2. So next we find the second derivative, so we're going to bring this negative 2 and multiply it to the negative 1 in front, and then subtract 1 from the exponent. So we end up getting 2 divided by x cubed. And when we plug in 1 for x, we get 2. Since we want to find the Taylor polynomial up to degree 3, that means we're going to let n equal 3 and do this one more time. And then we'll rewrite this as negative 6 over x to the 4th. And when we plug in 1 for x, we get negative 6. So for reference, again, this is the formula for the nth degree Taylor polynomial. So you have t sub n of x, and it equals f of a plus f prime of a over 1 factorial times x minus a to the 1, plus f double prime of a over 2 factorial times x minus a to the 2. And you continue that pattern until you stop with the nth term. So if you were trying to find t sub 0 of x, it would be equal to just f of a. If you wanted t sub 1 of x, you would include this term and this term as well. If you wanted t sub 2 of x, it would include these first 3 terms, and it would stop with this x minus a to the second power. So I wrote out the Taylor polynomial with degree 3. Part A is asking us to find the Taylor polynomial up to degree 3. So what that means is we want to identify t sub 0 of x, then we want to identify t sub 1, and then t sub 2, and then finally t sub 3. So in order to identify t sub 0 of x, it's equal to just this first term. So t sub 0 of x is equal to f of 1, and f of 1, according to our chart, is 1. So we have t sub 0 of x is equal to 1. T sub 1 of x is going to equal both of these terms. So it's going to have this f of 1, and then it's also going to have this term as well. Again, we already identified that f of 1 equals 1. And then for this term right here, we just need this f prime of 1, which we can get that from our chart. F prime of 1 equals negative 1. So when you plug in negative 1 right here, you get negative 1 divided by 1 factorial, which is negative 1 divided by 1, or just negative 1. And then you still have the x minus 1 expression. So t sub 1 of x equals 1 minus the quantity x minus 1. The second degree Taylor polynomial goes all the way out to this term right here. So we still include these first 2 terms, but we're also going to include this one right here. This f double prime of 1, we can get that from our chart. It equals 2. So it's going to be 2 divided by 2 factorial. 2 factorial is 2, so 2 divided by 2 is 1, so this is just 1. So here's our second degree Taylor polynomial. And then for our third degree Taylor polynomial, we still have these terms, and then we also need this one right here. So the third derivative of f at 1, according to our chart, is negative 6. So we plug that in right here, negative 6 divided by 3 factorial. Remember, 3 factorial is 3 times 2 times 1, which is 6. So the 6's cancel, and you just have negative and then this expression. So here we have all of our Taylor polynomials up to degree 3. And what we're going to do is we're going to look at the original function. Our original function is 1 over x. So let's go ahead and graph that on here. So to the right of the y-axis, here's our graph for 1 over x. And again, we're kind of focusing on this graph at x equals 1. So right in here. So next what we're going to do is we're going to graph these Taylor polynomials on this curve. So for our first one, t sub 0 of x, it's just equal to a constant value of 1. So t sub 0 hits the graph of f right at 1, but that's about it. This is clearly not a good representation of this curve at 1, so we'll keep going. For t sub 1 of x, we have 1 minus the quantity x minus 1. If you distribute this negative, you get negative x plus 1. So this equation ends up being negative x plus 2. Okay, so we're taking this t sub 1 of x, it hits the y-axis up 2, and the slope is down 1 over 1. And so you can see that this curve, this t sub 1 of x, is a nice tangent line to the graph of f at 1. And hopefully you're noticing if you're really close to 1, this tangent line can be a good approximation for the graph of f near 1. But as soon as you go away from 1 in either direction, this tangent line will be less of a good approximation for the actual curve. All right, so now let's go ahead and look at t sub 2. All right, I'm attempting to freehand these. So this t sub 2, you can see because it's a parabola, as you get close to the value 1, this curve is doing a nice job of resembling the original graph of f. But again, as you go more to the right or more to the left, the curve will go away from the actual graph of f. And then let's look at t sub 3. Okay, in our t sub 3, again, it's a cubic function. So I drew it here in purple to try to distinguish it from the others. And because it's a cubic function, it really nicely resembles the graph of f as you get close to 1. You can see that it's coasting along there and then goes down. All right, so the connection we're trying to make here is that the further out that you take your Taylor polynomial, the better it resembles the original curve at the designated value. And for part B, we're going to take some values for x, we're going to plug them into the original function 1 over x, and we're going to compare those with plugging in the values into our Taylor polynomials to further exemplify that the further out you take your Taylor polynomial, the better the approximation is of the value. All right, so we're going to start with x equals 0.9. We're going to take 0.9, plug it into the original function, and again, the original function is 1 over x, so we're going to go 1 divided by 0.9. And on the calculator, you get 1.1 repeating. Now we're going to take this value and we're going to plug it into t sub 0, t sub 1, t sub 2, and t sub 3. Since t sub 0 is a constant value, when you try to plug in 0.9, you can't plug anything in, you just get out the value 1. When you plug in 0.9 to t sub 1, we plug the 0.9 right here. When you simplify it, you get 1.1. When we take 0.9 and we plug it in here for t sub 2, we're plugging in 0.9 for this x and this one, plug it all into a calculator, and you get 1.11. Similarly, when we plug in 0.9 to t sub 3, you get 1.111. So again, plugging in 0.9 to the actual function, we got 1.1 repeating. And as you're plugging in 0.9 into the higher power Taylor polynomials, the values that you are getting out are more closely resembling the actual value f of 0.9. We're going to do the same thing with x equals 1.3. We're plugging it into the original function, so we're going to go 1 divided by 1.3, and you get 0.769. Again, when you plug in 1.3 to this constant, you just get that constant. Then we take 1.3 and plug it in right here for t sub 1, and you get 0.7. Plugging in 1.3 into t sub 2, we plug that in here, and you get 0.79. And finally, t sub 3 of 1.3 is 0.763. So again, as we plug in 1.3 into our Taylor polynomials, the further out the polynomial goes, this value more closely resembles the actual value of the function at 1.3. So I just wrote a note, as n increases, t sub n of x is a better approximation for f of x. This example says, let f be a function given by f of x equals ln of 3 minus x. The third degree Taylor polynomial for f about x equals 2 is, so first I set up our chart to take our derivatives. We're going to start with n equals 0. So that's just going to be the original function, natural log of 3 minus x. And since the Taylor polynomial for f is centered about x equals 2, we're going to plug in 2 for x right here. So 3 minus 2 is 1. The natural log of 1 is 0. So I have that written here in the last column. Next, n is equal to 1. So we're going to take the derivative of this. So we have ln of 3 minus x. The derivative is going to be 1 over 3 minus x. And then we chain rule. The derivative of the inside is negative 1. So we'll multiply that on top. So next we're going to plug in 2 for x. We get 3 minus 2 is 1. So we end up getting negative 1 over 1, which is negative 1. Next we're going to take the second derivative. I kind of squeezed this in here, but I rewrote this expression as negative and then the quantity 3 minus x to the negative 1. To take the derivative, we're going to take this negative 1, multiply it to the negative in front. So that just becomes positive 1. Leave the inside the same, subtract 1 from the exponent, and then we times by the derivative of the inside, which is negative 1. So I just squeezed a negative 1 right there. All right, and then I rewrote this as -1 over the quantity 3 minus x squared. So now when we plug in 2 for x, we get 3 minus 2 is 1, 1 squared is 1, and then we get -1 over 1, which is -1. Okay, finally we're going to take the third derivative. So I just squeezed the negative right there, and I rewrote it as -2 over the quantity 3 minus x cubed. Now we're going to plug in 2 for x, so 3 minus 2 is 1, 1 cubed is 1, and we end up getting -2 over 1, which is just -2. All right, we want a third degree Taylor polynomial for f about x equals 2. So I'm going to write out the formula. So here's our third degree Taylor polynomial written out. And again, we're going to take the values in this right column and we're going to plug them in right here in the numerators. So f of 2 is equal to 0. F prime of 2 is -1. So -1 over 1 factorial is just -1. And then I dropped down this x minus 2 to the 1 right here. F double prime of 2 is going to be this -1 right here, so we'll plug in -1. -1 over 2 factorial is the same as -1/2. And then we just drop down this x minus 2 quantity squared. And then the third derivative of f at 2 is right here, it's -2. So we plug in -2 here. Remember 3 factorial represents 3 times 2 times 1, so the 2's are going to cancel and you're left with -1/3. And then we drop down this x minus 2 quantity cubed. All right, so here's our third degree Taylor polynomial, and this matches with answer choice B. All right, so there's our answer. This example says, let f be a function having derivatives of all orders for x greater than 0, such that f of 3 is 2, f prime of 3 is -1, f double prime of 3 is 6, and the third derivative of f of 3 is 12. Which of the following is the third degree Taylor polynomial for f about x equals 3? So I wrote out our third degree Taylor polynomial for f about x equals 3. So you can see I plugged in 3 for all the a values. So hopefully by now you're getting really comfortable with this formula. And then at this point we're going to take these values and plug them in. All right, so our answer is D. This example says, let p of x equal 3 minus 3x squared plus 6x to the fourth be the fourth degree Taylor polynomial for the function f about x equals 0. What is the value of the fourth derivative of f of 0? So since we know that this is a Taylor polynomial of fourth degree for a function of f about 0, and we need the value of the fourth derivative of f at 0, we want to focus in on this term right here. So I want to look back at the Taylor polynomial formula, and let's look at this term right here. It says f second derivative of a over 2 factorial, and then it's times x minus a to the 2. So the important thing that's happening here is when we have a term that has x to the second power, the coefficient is the second derivative of f at a divided by 2 factorial. Or you can look at the general term. Here you have x to the n, and then the coefficient is the nth derivative of f at a divided by n factorial. So what that means for this term right here, you have your x to the fourth, and the coefficient of 6 is equal to the fourth derivative of f of 0 divided by 4 factorial. So we can set the formula for the coefficient equal to positive 6. And since the problem is asking for just the value of the fourth derivative of f, you can see that that's right here. So to isolate it, we're going to multiply both sides of this equation by 4 factorial. So we get that the fourth derivative of f of 0 is equal to 6 times 4 factorial. And remember, 4 factorial is 4 times 3 times 2 times 1. So when we multiply 6 by 4 factorial, it's 6 times 24, which is 144. So our answer is A. Next, we're going to shift gears and talk about error. It says 3 methods for estimating the size of the error. Number 1, use a graphing calculator to graph absolute value of r sub n of x, where the error is represented by the absolute value of the actual function minus the Taylor polynomial, and then estimate the error. Number 2, if the series is an alternating series, use the alternating series estimation theorem, where we have if s is equal to sigma -1 to the n minus 1 b sub n is the sum of an alternating series that satisfies the two conditions where the terms are decreasing and the limit as n gets larger of b sub n equals 0, then the error r sub n is equal to the total sum minus the nth partial sum, which is less than or equal to the next term b sub n plus 1. Number 3, in all cases we can use Taylor's inequality theorem or Lagrange error bound. Taylor's inequality theorem or Lagrange error bound. If we have the absolute value of the nth plus 1 derivative of f and it's less than or equal to m, then the absolute value of r sub n of x is less than or equal to m divided by n plus 1 factorial times the absolute value of x minus a raised to the power n plus 1. We can also refer to it in this formula right here, where again you have your error is less than or equal to, this is the nth plus 1 derivative divided by n plus 1 factorial times the quantity x minus a to the n plus 1. So r sub n of x is the remainder or the maximum error, and then this entire expression is the next term of the Taylor polynomial. Steps when calculating Lagrange error bound. You're going to consider this part of the formula and this part of the formula as two separate parts. Then we plug in a value of x within the given domain to each of these parts in order to make them as large as possible, therefore maximizing their product. We have a note, plugged in x values may be different from each other as long as they are both in the domain. So the value that you plug in for this part may be different than the value you plug in for this part. The main thing is we want to maximize this expression and we also want to maximize this one. This example says use the alternating series estimation theorem to estimate the range of the values of x for which the following approximation is accurate to within the following error. Check the answer graphically. So we have cosine of x is approximately equal to the fourth degree Taylor polynomial 1 minus x squared over 2 plus x to the fourth over 24. And we want to find a range of values of x such that the error of using this approximation is less than 0.005. So right now this Taylor polynomial has been taken out to degree 4. So we're calculating the error when n is equal to 4, and that's equal to the total sum minus this fourth partial sum. And this is less than or equal to the next term. So the next term, so according to this pattern, the next term would be represented by b sub 6. Remember, in this formula, this represents 2 factorial, this is 4 factorial, so the next term would be x to the 6th over 6 factorial. And again, this alternates, so technically the next term is negative x to the 6th over 6 factorial, but we're taking the absolute value of it and we're setting it less than 0.005. Okay, so we have this absolute value inequality. First thing, 6 factorial is 720. So I'm going to pull that out of the absolute value. And then next, we're going to multiply both sides of the equation by 720. So when we multiply 720 by 0.005, we get 3.6. And then at this point, we're going to raise both sides to the 1/6 power. So we get the absolute value of x is less than 1.238. And this becomes the interval from negative 1.238 to positive 1.238. All right, so here's our range of values of x. For our graphic representation of this, we're going to let y sub 1 equal the original function cosine of x, and y sub 2 is going to be the Taylor polynomial. So our y sub 1 is cosine of x, so I just started at a height of 1. It goes down to the right and then back up. Same thing to the left, goes down and then back up. It's supposed to be symmetric. When you graph y sub 2, the degree is 4, so to the right and the left the graph goes up. And when you're using your graphing calculator, you can hit trace and you can kind of move your cursor along the curves. And you'll notice that the interval over which the two curves really closely resemble each other, it's going to be very close to this interval. This example says given f of x, which equals x to the 1/3, a equals 8, n is 2, and then we have the closed interval from 7 to 9. Part A, approximate f by a Taylor polynomial with degree n at a. So setting up our chart, we're going to start with n equals 0. So that means we're going to take the original function. And then a is equal to 8, so we're going to plug in 8 for x. The cube root of 8 is 2. So we're putting that in our right column. And now we'll start the process again. We're going to do n equals 1. So we're going to take the first derivative. And we get 1 over 3 times x to the 2/3. When we plug in 8, the cube root of 8 is 2. 2 squared is 4, so 4 times 3 is going to be 1/12. Next, we have n is equal to 2, so we're going to take the second derivative. So we get negative 2 over 9x to the 5/3, and we plug in 8. Cube root of 8 is 2. 2 to the 5th is 32. Then the 2 and the 32 cancel, so you just have negative 1 over 16 times 9. So you get negative 1 over 144. Even though we're going to write a Taylor polynomial for degree n where n is 2, I'm going to do one more derivative just because of what's going to follow in the next part of the problem. And we get 10 over 27 x to the 8/3. All right, now we're ready to write our second degree Taylor polynomial. And again, the Taylor polynomial is at a, and a is 8. So I got that written out. Now we're going to take these values on the right column and we're going to plug them in for the numerator of each term. So f of 8 is 2, f prime of 8 is 1/12, f double prime of 8 is negative 1 over 144. So that value is going to go right here, but we're still dividing by 2 factorial, which is the same as dividing by 2. So that's negative 1 over 288, and then we still have this x minus 8 to the second power. All right, there's our Taylor polynomial degree 2, and it's centered at 8. Part B says use Taylor's inequality to estimate the accuracy of the approximation f of x is approximately equal to our second degree Taylor polynomial when x lies in the given interval. So our interval is from 7 to 9. And again, because n is 2, it's a second degree Taylor polynomial, which again we identified right here. All right, so Taylor's inequality, or a Lagrange error bound, is using this formula right here. And since we found the second degree Taylor polynomial, we're calculating r sub 2 of x. Since n is equal to 2, this is going to be the third derivative of f, and we divide that by 3 factorial. And over here, a is equal to 8, so it's x minus 8 to the power of 3. And again, our domain is from 7 to 9. So first what I want to do is I want to plug in this third derivative, and we calculated that up here. So here's our third derivative, 10 over 27, x to the 8 thirds. So again, for this expression, we have 10 over 27. It's x to the 8 thirds, but instead of x, we're using the letter c just to represent a constant that we're going to plug in. And then we're still dividing by this 3 factorial right there. And then I just dropped this x minus 8 to the third power down. So next we're trying to maximize this product. We want to think of this as one part and then this as a separate part. We're going to choose a value in this domain to plug into this part of the problem, and then we're also picking a value from this domain to plug into this part of the problem with the goal that we're maximizing both of them. So for this part on the left, you can see that the c value is in the denominator. In order to maximize this, we want to plug in the smallest value. So over this domain, that's going to be the value 7. So we have 10 over 27 times 7 to the 8 thirds times 3 factorial. So one more time, just because of the specific problem where the c value is in the denominator, we chose the smallest value of this domain to plug in to keep this at its largest value. If this c value was in the numerator, we would have picked the largest value, which would have been 9. Over here, again, this is a separate part. It's in the numerator technically, so we want to pick the largest value, so we're going to plug in 9. And now that we plugged in 7 right here and we plugged in 9 over here, we're going to take this entire expression and plug it straight into the calculator. And we get that the error is at most 0.000344. And I just wrote it out. Therefore, the second degree Taylor polynomial of f, which equals x to the 1/3, varies from the actual function on the closed interval from 7 to 9 by at most 0.000344. Part C, check your result in Part B by graphing r sub n of x. So the absolute value of our r sub 2 of x, or our error, is equal to the absolute value of, and this is the original function for f, minus, and then this is the second degree Taylor polynomial of f. I put this into the graphing calculator, and you can see the curve is right here, and I wrote out the viewing window over here. So in the x direction, it's from 7 to 9, and then I went from negative 0.00005 to 0.0003. And then I used the trace button. As I got over here closer and closer to 7, it reaches a height of 0.00026. And then over here, as you get closer and closer to x equals 9, you're at a height of 0.00022. So again, the error we calculated was going to be less than or equal to 0.000344. But here we have it demonstrated graphically. Alright guys, thanks so much for watching, and please subscribe to my YouTube channel, Math with Yosh, and hit the like button. I appreciate it.